Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. So today we're going to begin again by reviewing our basic probability model, which looks something like this. So imagine I've got some sample space possibilities, which we call omega. And I've got two events of interest, let's say A and B. In this setting, because there's no overlap, we say that A and B are disjoint or mutually exclusive. And in this setting, we have a nice fact that we should always remember, which says that if A and B are disjoint, which is the same thing as mutually exclusive, then probability of A or B happening is equal to the sum. We'll see that later in general. The formula goes something more like this, which is that take the sum of those probabilities, and then I have to subtract probability of both events happening. Because in effect, we end up double counting if we don't do this additional subtraction. So under the disjoint hypothesis, we have this formula. But then we also have in general. So let's look at one special case of this formula, namely in the setting where, so let's look at A and B is equal to A complement. In this setting, if you recall, A complement is just everything that's not A, including B. So this is A complement. And in this setting, we now have that probability of A union A complement, which is the probability of anything happening, is equal to 1. But by this formula over here, this has to also be equal to probability of A plus probability of A complement, which leads to the useful formula that probability of A can be determined by 1 minus the probability of A complement. We sometimes call this the law of complements. So let's look at perhaps the most famous situation where the law of complements is extremely useful. This is sometimes called the birthday problem or birthday paradox. Put scare quotes around paradox because this isn't actually a paradox in the sense that it shows some sort of deep conflict within mathematics. It's what's called a falsitical paradox, or just a paradox which is more counter to intuition rather than, or maybe it's just surprising, rather than something that shows some deep internal struggle. And it goes something like this. So the question is, what is the probability of at least 2 people in a room or a class of size n having the same birthday? By this birthday, we literally mean day of the year. So it doesn't matter if someone was born in 1999 or 1985 or what have you. You just care about the month and day. This actually is a hard question to maybe answer directly, but it's best to then think about what's the opposite. So we call this event A. So two people in the class of size n having the same birthday, we're going to call that event A. Which begs the question, what is omega? So what is our space of possibilities? So here's a further question. So I'm going to think of, so here, omega is the space of possible birthdays. I'll say birthday ensembles or maybe assignments. And again, in discrete probability, the first thing you need to do is figure out how big is omega. So we have to come up with a way of counting the size of omega. And so it helps to put a little bit of structure on the problem. So imagine we've got student 1, student 2, on the way up to student n. And we can think of each birthday for each student. So let's look at this maps to birthday of student 1 on down through birthday of student n. Well, each of these has a possibility in between, January 1st and December 31st, of which there are obviously 365 possibilities. So every person gets a birthday. And, conceivably, we could have a class where literally everyone was born on January 1st. It's highly unlikely, but it's still a possibility. And it needs to be accounted for in describing omega. So the rule of multiplication tells us that the size of omega is 365, because that's the possible birthdays for the first student, on down through 365 possibilities for the nth student. So you have to do this n times, which is equal to 365 to the n. So how do we figure out this problem? Well, it turns out it's actually better to think about the complements. And so on the next page here, I've gone ahead and included a graph of this probability curve as a function of the number of students, meaning as a function of n. So we can think of this as n. Let me switch back to my black color here. So there's this n, this is our number of students. And so what's happening here is we're seeing a graph of the probability of a complement. And so how do we figure out what this curve is? How did I produce this curve? Well, remember what a complement is. This is the event where no two students have the same birthday. So how do we do that? Well, notice that when I was modeling the problem, I didn't use people's names. I said student 1, student 2, on through student n. That actually encodes some extra information where I've ordered the students. You might ask, how do I rank students? Well, one way of doing that was I could say, look at their names and then just order them alphabetically, looking at second and third letters to break ties. So there's actually no harm in ordering my students in this situation. But later in this class, we're going to see where that assumption actually matters. But let's go ahead and figure out, what is the size of a complement? Well, we need to first recognize that student 1 has 365 possible days that their birthday could lie on. It doesn't really there's no exclusions at that point. But then as we go to the second student, student 2, we have to exclude whatever birthday was taken by student 1. And so we keep going down through 365 minus n plus 1. And again, that sort of plus 1 just comes down to the fact that, think about it, if there's only one person in my class, that means n is equal to 1, then there's 365 possibilities. So this is what results in the case where n equals 1. So you just double check small numbers to make sure that this formula makes sense. So we learned in in class that there's another way of writing down this number in a more compact description. And it's to write it something like this. So we do 365 factorial divided by 365 minus n factorial. Because this top number here looks like factorial if I were to keep going all the way down to 1. So the way of canceling out whichever number would have come next, which is 365 minus n, on down through here, I then use this expression to cancel those out. So what is this curve that I've drawn here? Well, this curve above is the graph of 365 factorial divided by 365 minus n factorial, all divided by 365 to the n. Because this is probability of A complement, which in turn is just equal to the size of A complement divided by the size of our space of possibilities. And we're working in a situation where essentially we think of every assignment of possibilities of birthdays being equally likely. We're not taking into account that maybe more people are born in January or what have you, which is sort of a function of season and things like this. We're ignoring all of that and just trying to take the most naive, direct approach to this problem. You'll notice that this curve up here above has something that almost looks like kind of like a phase transition. To exaggerate what a phase transition would look like this, and then it would have a rapid change. This is a little more gradual, but you'll still notice that there's something sort of rapid that's about this. And in fact, around 22 or 23 students, you'll see that the probability of there being at least 2 people with common birthdays goes from being less than 50% to more than 50%, where I then take 1 minus this curve to get the probability of A. So we'll eventually figure out what a really good approximate formula for this curve is. And notice that it looks continuous, even though the number of students is a sort of a discrete quantity. This curve doesn't seem too jagged. It's not something that steps down like this or anything like that. And we'll see why that is in a future class. But anyhow, one question I want you to think about is if you look at this, notice that by the time we get to, I don't know, around 60 students, which if I've got this sort of spreadsheet version of this up in front of me, you see that there's actually less than a 5% chance, even less, so less than a 0.5% chance of there being no students with the same birthday. That's up here around 60, I believe. Yep, so around 60 here. We're already down below 1%. In fact, that transition happens around 55, I think. Now, can you give me a situation where you know for certain that there has to be at least two people with the same birthday. So if you think about that for a little bit, you realize there is one situation, and you can see it just by looking at this formula, which is what happens when n is larger than 365. What happens in that denominator is we're now looking at a negative number. We don't really know what negative factorial is supposed to be like. But we understand that actually by convention, if you start to multiply and you want to go down below 0, then you should just be multiplying by 0. So what ends up happening is that this probability goes to 0. Probability of a complement equals 0 for n greater than 365. Now this should sort of make sense to you, because imagine I've got, 365, let's say 366 students in my class. Then it stands to reason that at least 2 of them are going to have the same birthday, because the set of possibilities of birthdays is only 365. And if I'm trying to avoid each birthday as I go down and I continue doing this subtraction up above, eventually, if I assumed that everyone had distinct birthdays, by the time I get to the 366th person, one of the birthdays has to repeat, because there's only 365 days in a year. This is sometimes called the Pigeonhole Principle. And the picture goes something like this. Like, imagine I've got, all right, now they look like little dinosaurs, and I'm just going to roll with it. All right, so maybe I should call this the dinosaur principle. So imagine I've got I've got 3 dinosaurs. All right, that one kind of looks more like a pigeon, which I guess just proves to you that birds are the modern day descendants of dinosaurs. And imagine they're trying to, enter in to a box where they're, let's have this tree here, and inside of here I've got their sort of a pigeon house. But there's only 2 doors. All right, and imagine there's a little chimney. So here's door 1 and door 2. If you ask yourself, well, how can these dinosaurs these modern day dinosaurs enter into this house? You'll recognize that because there are only 2 doors and 3 dinosaurs, then no matter how it goes, at least 2 have to go through one of the 2 doors. So said in writing, if the number of pigeons is strictly greater than the number of holes, then at least 2 pigeons must go through the same hole. Now, of course, I could have increased the number of holes and the number of pigeons. Here I just had 3 and 2. There's sort of a general statement that says something like this. So if I do like my generalized pigeonhole principle, says something like this. If there are n pigeons and m holes, then n divided by m, where I then take the ceiling, so I think of this as the ceiling of n divided by m, pigeons must go through So for example, if I, instead of just having these 3 up here, I had, a total of 5 pigeons. All right, there's my 5 additional pigeons, and they started going through the holes, then I would have at least 3 of them had to go through the same hole, because, even if the first 2 evenly went through the hole separately, the 5th pigeon would have to go through at least one of the doors that the other 2 went through, and that door would then have a count of at least 3. As an application to our birthday problem, if I were lecturing in a huge lecture hall, and that lecture hall had something like, I don't know, 800 students, then at least 3 students would have to have the same birthday. And you do that just by taking 800 divided by 365. That's the holes or possibilities. And I take the ceiling of that. Well, 730 would be 2 times 365. So the second I'm at a little bit above 730, 731, then I know that at least 3 people have to have the same birthday. So these are instances where I can say probability 1 or probability 0 events. And this is a common sort of principle in combinatorics, which I want you to be familiar with. All right, so we just revisited the birthday problem. We illustrated an example where we can say for certainty that at least 2 people have the same birthday by virtue of the pigeonhole principle. Let's revisit one of the other sort of canonical tools for counting and thinking about discrete probability. So this is our sort of back to the urns. And so let me do this. And I'm going to call this sampling. So back to the urn. Again, this is our urn, where there's our sort of whole space of possibilities inside of here. And last time we considered an example of drawing without replacement or sampling without replacement, but where the order mattered. So I imagine drawing 1 ball at a time, and it was very important that I remembered which ball I drew first. So let's vary the vary this problem slightly by considering sampling without replacement where order does not matter. sort of last time we considered it where order does matter. And so here's the typical problem. So it's a typical problem here. I'm gonna actually briefly erase one of these guys. So here we imagine we've got so we have an urn with 5 unique balls. And so you can imagine each of these has a different color. And now you're going to think of these maybe as a, let's say we're going to ask, what's the probability of drawing out the green ball, assuming they all have different colors, urn with 5 unique balls, all different colors. And let's describe the experiment here. We're not just going to reach in once and pick out a ball and ask what's the probability of getting the green ball. Instead, what we want to do is reach in and grab a bag of 3 and then look at the 3 that are inside of our hand and ask, what's the probability that one of them is green? So here's our experiment. This is the thing that then lands us into a space of possibilities indexed by omega. So we draw 3 balls once. And the event that we're interested in is drawing the green ball. And so we're going to call that our event A. So of course, the question is, what's the probability of A? So the first thing we need to do is identify what is the space of possibilities. So answer we have to identify the space of possibilities, omega. Again, we call this the sample space. So you need to figure out how many size 3 subsets are there when I'm drawing from 5 distinct objects. So here, we think of this as, so we're gonna have to identify, I'm sorry, I used blue usually for talking about this, but here omega is gonna be the set of size 3 subsets from a 5-element set. And so we could think of that 5-element set, here I use colors, but could also think of this as 1, 2, 3, 4, 5, where I rank them, say, by my favorite color. And now I'm just asking, well, how many size 3 subsets are there of 1 through 5? So this is where we get one of the most important formulas. So this is determined by what's called the choose formula. What it says in this particular example is that the size of omega equals the number of size 3 subsets of a 5-element set. And the way we write this is we say something like 5 choose 3 stacked on top of each other with these big round brackets. Now what this is a formula for is 5 factorial divided by 3 factorial times 2 factorial, all on the bottom, which in this case happens to be 5 times 4, because 3 factorial got canceled out by the 3 factorial here, and then times 2 times 1. So this just illustrates some of those cancellations. And so we're led to the formula that there are, well, 20 divided by 2, which is 10 size 3 subsets. Now, let me just briefly comment on what would be the wrong way of thinking about this. The wrong way. Wrong way would say, okay, I've got 5 options for my first set. So I'm going to be, that gives me 5. And then I have 4 remaining options for my second element that I choose. So that gives me already 20. And then I multiply this by the number of options remaining for my third element, which is there are 3. And so if I do that all, I'll get 5 times 4 times 3 is 12 times 5, which is 60. Now, the reason why this is wrong is because I'm imposing an order. I'm thinking of there as being the first object I've drawn, the second object I've drawn, the third object I've drawn. And so what I need to do is actually cancel out by the number of permutations. So there are 3 factorial, which equals 6 ways of permuting this. So if I want to fix the formula, I have to end up dividing by 3 factorial. And that gives me 10. So that's going to be the right way. Anyhow, that tells us how big omega is. But now we need to figure out, well, how many ways are there of drawing a size 3 subset where there's the green ball in my size 3 subset. So switching back to black here. So remember A, I think of as being the event where the green ball is in my size 5 subset. So how many ways are there of doing that? Well, let's say that, green is my favorite color. So I think of this as being, I'm forcing that I draw 1. So I'm going to make that correspond to green. And then, what other colors did I have here? I think blue is probably my second favorite color, and orange as being my blue is my second. Orange being my third. Maybe red being my fourth favorite color. And then purple being my least favorite color. Just to make sure that there's some correspondence between colors and numbers. But anyhow, if I go through and I do that and I ask, well, first I want 1 to be in my size 3 subset. So now how many size 2 subsets are there of my remaining 4 elements? Well, again, I have this situation where I can think of drawing, so I'll just write it this way, any size 2 subset of 2, 3, 4, and 5. So how do I do that? Well, I got to pick one element. So that's 4 elements. And then I pick another element. So there's 3 to choose from. That gives me 6. But there again, I've implicitly used order. So I need to divide by 2. So you can also just write it out. Well, so the size of A is going to be the number of size 2 subsets of my remaining colors, 2, 3, 4, and 5. So if I try to sort of mimic this formula, it's 4 factorial over 2 factorial, 2 factorial, which is 4 times 3 divided by 2, which is 6. So all this is to say that to answer my problem, probability of A, in this case, ends up equaling 6 divided by 10. So it's a 60% chance. Now you might be asking, again, what's the sort of general formula here? It's going into our choose formula. I'll go ahead and write it here. So n choose k equals n factorial divided by n minus k factorial times k factorial. And I'll write that again a few other times. All right. So let's imagine we do another sort of similar example. More examples. With our urn. So here, imagine we've got an urn. And we've got 3 green and 4 yellow balls. All right, so we've got a three green and 4 yellow balls. 3 green and 4 yellow balls. Side of our urn. And imagine we want to do now is we want to draw 2 without replacement. Again, what that means is that if I draw 1 out, I don't put it back in, so that like if, for example, I draw a green ball, it reduces the chance that on the next draw, that's also a green ball. So let's first try to. So here's a question. So how do we describe the possible outcomes of this experiment? Where again, this is the experiment here. So a good way of modeling this is to first say something like, all right, let's imagine we can label the balls in such a way that we make each one of them distinct in some other way. You imagine there are little scratches on the green balls, which indicate that we can actually tell apart what the three green balls look like. So what we do, we have something like S is our set of green balls, or a set of balls. There's green number 1, green number 2, green number 3, yellow number 1, yellow number 2, yellow number 3, yellow number 4. And so our space of possible outcomes which goes into omega is a set of subsets. I don't know, call it a B side of S, such that the size of B is equal to 2. Well, we can use the choose formula now to figure out what the size of omega is, which is that there are 7 possibilities, and then we're drawing 2 from them. So 7 choose 2, which written out mathematically, we need to take 7 minus 2 factorial, so that's 5 factorial, and then times 2 factorial in the bottom. So this ends up being 7 times 6, and then the 5 ends up being canceled, and then again dividing by 2. So this equals 21. Now, suppose we're interested in an event. So now we have an event. So suppose A is the event that the 2 balls have different colors. So how do we figure out the probability of A? So compute the probability of A. Well, the answer then is I need to take the probability of A is equal to the number of ways in which A can occur divided by the number of total possible outcomes, which we just calculated above was 21. So what do we get here? Well, to figure out this, we need to first draw a green ball, and then we need to draw a yellow ball. So how many ways are there of drawing a green ball? Well, there are 3 choose 1 ways of drawing the green ball. So this is our number of ways of drawing 1 green. And then over here, I have the number of ways drawing 1 yellow. And again, this is from the fact that there are 3 green and from 4 yellow. So that equals 12. So this means that the probability of A occurring is, well, I counted that there were 12 ways of drawing 1 green and 1 yellow out of the total possible number of subsets, 21. Now, there's some sort of subtlety here where you need to ask yourself, when I wrote this number 3 times 4, was I maybe overcounting or undercounting the possibilities? So meaning, was I sort of imposing order on the problem that wasn't really there? So let me sort of step back and reconsider the broader question of what is the difference between ordered and unordered samples? So question. Write it this way. So, ordered versus unordered. Samples. So often, when we do this sort of thing where I ask students, and I've asked the first student what their birthday is, and then I go on to ask the second student what their birthday is, and things like this. You could ask yourself, well, in that process of talking about the first and the second and so on, did I impose extra order that wasn't really intrinsic to the problem? So I'll argue in that setting, the answer is no. I didn't actually introduce any unnecessary order, because all the students are unique. They have names, and I can kind of separate them out accordingly. But in other examples, for example, when you play cards in your Delta 5 card hand, this way of sort of asking, well, how many 5-card hands there are, you often begin by imposing order on the problem, which you then want to purposely forget. And the way we do this is by dividing by the number of permutations of that sort of imposed order that was sort of a crutch for thinking. So just remember here, so here's an important formula. So when we talked about, maybe just sort of summarize up top here, when we talked about samples without replacement, and so here we think of this as sampling K objects drawn from N objects. In the sort of ordered setting, we had this. We did n factorial divided by n minus k factorial. And over here, what we had to do was n factorial divided by, it's sometimes called n lower by k. And this is n factorial times n minus k factorial divided by k factorial. And so this is big N over k. Sorry, just little n over k, but stacked in a different way. So again, what this is shorthand for is, this is n times n minus 1 times all the way up through n minus k plus 1. Whereas this, on the other hand, is n times n minus 1 on down through n minus k plus 1. But then we're further divided. So first notice that the number of objects here that are k. So there's there are k factors here. So 1, 2. This is the first factor. This is the second factor. And this is the kth factor. This is the first, second, all the way down to the kth. But then I need to further divide by k factorial, because this is the number of ways of rearranging the k drawn elements. So let's look at an example here. So if I draw 5 cards, from a 52 card deck, well, for the first possibility, I've got 52 possible cards I could get. And then for the second, I've got 51. And then for the third, I've got 50. And for the fourth, I have 49. And then for the fifth, I've got 48. Notice that 48 is only 4 less than 52, even though it's the 5th card. So again, that's where that k plus 1 comes from. So third, fourth, 5th. So you might be led to believe that this is the number of 5 card hands from a 52 card deck, but it's not. We did that just to help think about what the space of possibilities was. So then we need to divide by the number of permutations of these 5 objects, because if I'm dealt these 5 cards and I shuffle them in my hand, I still have the same hand. So the number of ways of shuffling 5 cards, so you divide by 5 factorial, which equals 60. Is the number of permutations of a 5 card hand, or I should just say of 5 objects. Which should sort of give you a sense of why is the choose formula true. The choose formula is true, and this is, again, this right here is the choose formula, which you only use in settings where order doesn't matter. And this is the n lowered by k, which I won't really call anything special. Sometimes it's also called p and k. With the choose formula, you sample your k objects, and then you need to count also the number of ways of rearrangement, because that doesn't actually matter. But for example, in tarot, it did matter, which was your first card, your second card, your third card, because one determined your past, the second determined your present, and the third determined your future. And if you switch those cards up, then you get completely different readings. So then the question is really, what order matters to the game? So this idea that the number of permutations is counted by a factorial also gives you another way of thinking about why the choose formula is true. So why is the choose formula true? So imagine you've got n objects, which we'll just label x1, x2, on through xn. Now the number of permutations of these n objects is n factorial. So how might you choose a size k subset? Well, you could do some random permutation of these n objects, and maybe I'll just so how to choose k. So first I apply a permutation. Maybe I'll call that x sigma 1, x sigma 2, through x sigma n. And then what I'll do is I'll look at the first K and I'll cut. And that will be the K in my subset. But now I need to consider how many different permutations would give me the same subset. Well, obviously, if I have K factorial perms give the same subset, of the first K objects, but also I can permute anything that was left. I have n minus K factorial perms give the same complement. Then I can see why the choose formula, which is sometimes called CNK, first counts total number of permutations, but then I divide out by the number of permutations that give me the same subset via this algorithm for choosing a size K subset. So by taking n factorial permutations and then recognizing that amongst all of those permutations, which there are n factorial many, there are then going to be K factorial of those that give the same subset just by rearranging the elements in your hand. And then similarly in the deck of cards, you can permute any of the n minus K elements that were not in your hand. And that will also give you the same hand. So by taking n factorial and then dividing out the number of permutations that leave you with the same result, you then get the answer. All right, so that's effectively it for today. I look forward to seeing you in class.